Let's continue on and talk about some more of these problems from chapter 5, just how to start them, not necessarily how to solve them. So for this one, this is a very classic physics problem called the Atwood's machine. It's basically just two masses hanging from a pulley. At this point, we have a massless, frictionless pulley, so we don't really have to deal with any torques or anything like that with the pulley. We're just really dealing with two masses. So let me show you the setup for like the more standard way, and then I'll just show you like the quick and easy way to do it. So the standard way to do it would be to draw free body diagrams for each mass. So here's M1. I would draw force of gravity and tension. That's what's going on with M1. M2 over here, same free body diagram, force of gravity and tension. Now these tensions are the same because it's the same rope that's going through. These forces of gravity are not the same, but this one is just going to be M1 times G, and this is going to be M2 times G. Remembering, of course, that force of gravity is just M times G. So now I would write a net force equation for this one and a net force equation for this one. So over here, something I need to talk to you about is direction. So we're going to choose a positive direction. We're going to keep that direction the same way throughout the whole problem. So I'm going to choose plus as going up here, but because of this pulley, plus is also going to be going this way on this side. So here's the positive direction, going down like this on this side. What that means is in my net force equations over here, I want to write net force equals mass times acceleration, m1a, since it's the first mass. This is going to be a positive number, and this will be a negative number. So I'll add this and subtract this. That means T minus m1g equals m1a. Okay, on this one, once again, F net equals m2a. And now this is my positive force, and this is my negative force, because the positive direction on this side is going down. So I'm going to say m2g minus t equals m2a. Now, ultimately, we're looking for the acceleration and then the tension. So finding the acceleration and the tension, we've got two equations and two unknowns, and we would just have to solve those simultaneously, which isn't so hard. But let me show you the kind of quicker way to do this, and a little less formal. You should still know how to do this, but to make it easy, I can just combine those boxes together, and I can just call this M1 plus M2. What I'm doing here is just kind of acknowledging that the tension is just kind of a go-between. And eventually we're going to cancel out the tension anyway, so we don't really need it in there. And then the trick is, I'm going to have a force to the right here that's going to be this one, because that's pulling down here, going to the right. So this is going to be M2G. And over on this side, I'm going to have M1G, right? Because that's the force that's happening over here. So I've got an M2G and an M1G. And here, let me just move it down to this paper down here. So now I just write F net equals MA. So let's keep this the positive direction, this the negative direction. And I'm going to get M2G minus M1G equals mass, I should write down, F net equals MA. So I have to have the masses together, M1 plus M2 times A. And now I can just write out A equals M2G minus M1G divided by M1 plus M2. And there's what my acceleration is going to be. Now it's automatically going to give you the right direction for it. So depending on whether M1 or M2 is greater than the other one, it's going to determine which way this thing goes. And if M1 happens to be greater, it's going to give me a negative number, which means the thing is accelerating in this direction, which is my negative direction. So it's kind of already automatically done that. By the way, I guess you could simplify this to M2 minus M1 times G divided by M1 plus M2. Okay, so once you have the acceleration, now I can just go back and choose either of these equations to figure out the tension. Plugging the acceleration there and get the tension, or over there and get the tension, and it should be the same for both of them. So there you go, that's how you do that Atwood's machine problem. Moving on to 55 over here. So this one, it's just important to draw free body diagrams for. So we've got two blocks. It's a frictionless table, that's nice. There's a force pushing on this left block, which is M1, and it's, we know what the magnitude is. We know what the masses are, and find the magnitude of the force between the blocks. And let's see, show that if a force is in the same magnitude F is applied to the smaller block, but in the opposite direction, the magnitude of the force between the blocks is 2.1. Okay, so force of the same magnitude, we're going to take this force and we're going to put it around on this side instead. Okay, and then which is not the same as the value. Explain the difference. Okay, that's actually pretty interesting. So how do we do this? Let's draw free body diagrams. Here's M1. Let's see. Yep, here's M1. And we have this force that's acting on it, F. We're going to have a gravity force, M1G. Oops, that's an M1G. And we're going to have a normal force, Fn. Don't really care about those so much because they're going to balance each other out. We don't have anything that's happening in this up and down direction. Let's see if I can focus a little bit. Okay, that's good. So it's great to draw these on here, but it's not totally necessary. And then the other thing that we're going to have is, because these two blocks are touching, M2 is putting a force back onto M1, and it's going to be going in this direction to the left. So I'm going to draw that over here, and I'm going to label that like maybe F2, 1, the force of block 2 on block 1. Good? Okay, now we're going to draw a free body diagram for M2. There's M2. Sometimes when you label it as M2, the label just gets in the way. So down here, I have M2G, and I've got a different normal force. Don't really care about those. This time the only force that's, since it's frictionless, the only force that's acting on this block is, this F is not touching M2. This F is only touching M1. But there is a force between the blocks. It's the force of block 1 on block 2. So I can write F1, 2. Now here's what Newton's third law says. Newton's third law says that this force and this force are equal in magnitude and opposite in direction. That's the whole thing that basically Newton's third law is trying to say, is that they're equal in magnitude in opposite directions. Every action has an equal and opposite reaction, is kind of what they say sometimes. So now we're finding the magnitude of the force between the blocks. So we're either looking for this one or this one. We know this F, so let's just write out our net force equations and see where we're going with this. So this one, net force equals M1A, since it's just M1 over here. Let's choose this as positive and this as negative. So I've got F minus F2, 1 equals M1A. And then over here, F net equals M2A. This is our force now, positive direction, F1, 2 equals M2A. And now I've got two equations and two unknowns again. So I've got, this is unknown, the acceleration is unknown, and then this number is unknown. So solve the simultaneous equations. This is a number that you know that's given in the problem. So whichever one you want to do, remember these two are the same. So this and this are the same. So if you want to, you can just take this, stick it in there, and then solve for acceleration, and you should have it. So then you're going to redo the problem, and you're going to redo the problem now with the force over here. So the free body diagrams are going to look different. You're going to get a different acceleration, and you have to explain why you have that acceleration is different. I'll just let you do that part and see if you can get the concept of it. Okay, so that was kind of a lot of work that I did for you, but you hopefully can finish it up. Let's look at 57. Here's the diagram for 57. Let's see here. There it is, good. So 57 looks like this, and you've got a ramp and you've got a mass, and this is M1 and M2. Frictionless plane, so that's nice. We don't have any friction on the plane. And we're really trying to find the acceleration, the direction of the acceleration, and we're trying to find the tension in the cord. So once again, here's the quick and easy way to figure this one out. I want to remind you all that when you have a box on a ramp, and I know this one's attached to a pulley and stuff, but the general idea about the box on a ramp is that gravity gets broken down into components, one into the ramp and one down the ramp. And the down the ramp one here is, this is our angle right there, is Fg sine theta. So the force of gravity pulling this down the ramp is going to be Fg sine theta, and that's for mass 1, so this is going to be m1g sine theta. Remember, force of gravity is mass times g. Okay, so we're going to do this the quick way. Remember how we solved this Atwood's machine problem by, oops, where are we here? By putting these boxes together. We're going to do the same thing with this problem over here. You could do it more formally, but we're going to just draw the boxes together. That's M1 plus M2. Pulling this way, that's this direction, that's going to be M2G. So I've got M2G pulling this way, and this way it's this force right here. I've got M1G sine theta, And now I just write my net force equation. F net equals ma, remembering that that mass is both masses together. Let's choose this direction to be positive. m2g minus m1g sine theta equals m1 plus m2 times a. And when you solve this out, you're going to get a, where did I put that other thing? You're going to get something real similar to this Atwood's machine problem, except, I mean, it's basically the same thing, you just have a sine theta stuck in there. m1g sine theta, right? So there's my m1g sine theta over here. So you'll be able to figure out what the acceleration is based upon the numbers in the problem. We're given the masses and the angle, and you can figure out the acceleration. Now, the direction of the acceleration is going to tell you which way it's going to go, because we chose the positive direction is this way. And if you get a positive number, that means it's accelerating this way. If you get a negative number, it's accelerating that way. Now, to figure out the tension, now we actually have to back up and sort of draw these individually. So let's draw this one just as an individual object. I've got m2g going down, and I've got tension going up. So I could write m2g minus tension equals m2a. That's just net force as mass times acceleration. Once you know the acceleration, you work backwards to figure out the tension. Okay, moving right along. I like these problems as well. So here's 58, and it has this guy in a chair, and he's pulling himself up. I'll just set you up. There's a lot of questions to answer here. I'm going to set you up with a couple things. It says, hint, a free body diagram can really help. So what we're going to assume is that this rope, I know it's attached to this chair, but we're just going to say the chair and the man are kind of one object altogether, because it even says the combined mass of the man and the chair is 95 kilograms. What that means is that there's going to be a force of tension pulling up on the guy-chair combo right there. Because the tension is the same in the whole rope, and because the guy's grabbing onto the rope, if he pulls on the rope, Newton's third law says the rope pulls on him. So he's pulling down on the rope's pulling up on him with the same tension force. So here's how we're going to draw this free body diagram. We're going to have mg going down, that's the force of gravity, and then we're going to have two tension forces going up that are equal to each other. And then he has an upward acceleration, so we're just writing F net equals ma. Let's call that the positive direction going up. So I would have 2t minus mg equals ma. Yep, and you know the acceleration, so you can find the tension. So that's actually pretty interesting. For this one, when it says, if the rope on the right extends to the ground and is pulled by the coworker, so here's the guy, right? He's holding onto the rope, but this time it's going onto the ground. The free body diagram of this whole thing is going to change a little bit, because now we only have one attachment point. So for the free body diagram for this second part is this, and now there's only one tension, and then there's mg going down, and you're going to have to solve the problem there. The reason why there's not two tensions, or maybe I should say the reason there is two tensions in the first problem, is because he's grabbing on to the rope right there, right? You can imagine maybe there's a box and there's a pulley with two ropes and they're both attached to the box. I think you would probably say, yeah, that makes sense that there's a tension here and a tension here. It's the same thing here. It's like just another attachment point right there, all right? So I guess the thing that I maybe kind of skipped over a little bit is, with what force magnitude must the man pull? His pull down is going to be the same as what the tension is. So when you're solving this for tension, you're actually finding the force that he's pulling down with. Once again, that's Newton's third law. He pulls down, the tension pulls up, and those are equal and opposite to each other. Lastly, what's the force on the ceiling from the pulley system? So pulleys are really interesting that if you've got a rope attached around a pulley, the tension is technically pulling on the pulley as well. That was a terrible drawing. Let me draw it again. There's my pulley. There's a rope coming down on this side, and there's a rope coming down on this side. So the tension, there's a tension force there that's pulling down, and there's a tension force there that's pulling down. So the pulley is experiencing 2t worth of force pulling it down, which consequently is attached to the roof, and that's what's pulling down on the roof. So for these parts over here, really your answer is 2t is the magnitude of the force on the ceiling, and you're getting different answers for t from all these different parts. Okay, so that's 58. Moving on to 59. There goes the lights in the room. Hold on. Let's see, should we end this video now, or should we move on and do, I think we've got too many more problems to move on with. So let's end this video now, and let's refocus that. And then the next video, I'll do the next couple problems.